Jupiter sits 5 times farther from the Sun than Earth. Its upper atmosphere should be cold and calm, with barely enough sunlight to stir anything. Instead, it runs hundreds of degrees hotter than physics allows. In 2022, a telescope built to study galaxies billions of light years away got pointed at this planet instead, a job it was never designed for. What it found broke 50 years of settled science. The energy that shouldn't be there. Back when NASA's Voyager probes flew past Jupiter in 1979, they measured the temperature of its upper atmosphere and got a number that made no sense. The gas up there sat close to 800 degrees Celsius, hundreds of degrees hotter than sunlight could possibly explain at that distance from the Sun. Every gas giant in the solar system shows the same pattern, and scientists eventually gave the problem a nickname, calling it the energy crisis, since something had to be feeding heat into these atmospheres from a source nobody could fully account for. The leading explanation pointed to the auroras. Jupiter has the strongest magnetic field of any planet in the solar system, tens of thousands of times stronger than Earth's own field. Charged particles get funneled down toward the poles along that field, crash into the atmosphere, and light up the auroras the same way particles from the Sun light up the northern lights on Earth. Researchers suspected that heat generated near the poles somehow spread out and warmed the entire planet. But ground-based telescopes could never track the process closely enough to prove it. The measurements kept coming back too blurry, too faint, or too inconsistent to settle the question. That gap in the evidence stayed open for over 4 decades. Spacecraft missions came and went, each one adding small pieces of data without ever capturing the full picture of how heat actually moved through Jupiter's upper layers. Then a telescope originally designed to look at the earliest galaxies in the universe got pointed at Jupiter instead, and the wait for real answers finally ended. The missions that couldn't finish the job, Jupiter has actually had more visitors than any other planet outside our own. The Pioneer probes flew past in the early 1970s, followed by Voyager, then the Galileo spacecraft, which orbited the planet for 8 years, starting in 1995. Cassini swung by on its way to Saturn, and Juno has been circling Jupiter since 2016, diving close to the clouds on a regular basis to study its interior and magnetic field. Each mission added something new, yet none of them ever solved the energy crisis or fully explained what drives activity in the upper atmosphere. Part of the problem came down to what each spacecraft was built to measure. Galileo and Juno carried instruments designed to study Jupiter's deep atmosphere, gravity field, and magnetic environment up close, not the faint infrared glow of gases sitting in the thin upper layers. Cassini's cameras were tuned for its own mission to Saturn and only had limited time to study Jupiter during its flyby. Ground-based telescopes on Earth could observe the upper atmosphere from a distance, but Earth's own atmosphere blurs and distorts incoming infrared light, making fine detail almost impossible to capture reliably. What Jupiter needed was an instrument sensitive enough to detect faint infrared signals, positioned far enough from Earth's atmosphere to avoid that blurring and precise enough to separate small features apart from the glare of a planet that bright. No spacecraft or ground-based telescope had managed to combine all 3 requirements at once. That combination finally arrived by accident, built for an entirely different purpose than studying planets in our own solar system. The telescope that wasn't built for this. The James Webb Space Telescope launched on Christmas Day in 2021 with a primary mission of studying the first stars and galaxies that formed after the Big Bang. Nobody designed it with Jupiter in mind, but a group of scientists working on something called the Early Release Science Program argued that Webb's instruments, tuned to detect faint infrared light from the edge of the observable universe, would also be powerful enough to reveal details in our own solar system that no other telescope could see. Their proposal was written years before Webb even launched, back in 2017, and it took real persistence to get approved. Jupiter is one of the brightest objects in the night sky, which sounds like an advantage, but bright targets can actually overwhelm sensitive instruments built to detect the faintest possible light from distant galaxies. Engineers had to prove Webb could handle a target that bright without damaging its detectors or drowning out the very details scientists wanted to see. If you're enjoying this breakdown, hit subscribe so you don't miss where this bracket goes next. In July 2022, the telescope pointed its near-infrared spectrograph directly at Jupiter, focusing on the region above its most famous feature, the Great Red Spot. Nobody expected the results to be dramatic. The team's own stated goal was almost dismissive, hoping only to confirm that this particular patch of atmosphere was as calm and uneventful as everyone assumed. What came back completely reversed that expectation, and it was only the first of several discoveries Webb would make about a planet scientists thought they already understood. The storm, older than anyone alive. The Great Red Spot itself deserves some context since it is the backdrop for one of Webb's biggest surprises. The storm is bigger than Earth, with winds recorded between roughly 270 and 425 miles per hour, up to 3.5 times faster than a tornado. Astronomers have tracked it continuously for at least 190 years. And some records suggest a similar dark spot may have been spotted even earlier, making it possibly the oldest continuously observed storm system in the solar system. The storm has also been shrinking. Telescope measurements going back over a century show the Great Red Spot slowly losing size, and observations in recent decades have shown that shrinking pace speeding up. Scientists do not fully agree on why the storm is losing ground, or whether it will eventually break apart entirely, which is part of why any new data about the region carries extra weight. A storm this large and this old interacting with the thin atmosphere sitting above it was exactly the kind of relationship researchers wanted to understand better. That is why the region above the Great Red Spot became an early target for Webb's early release science program in the first place. Researchers expected the upper atmosphere there to be shaped mainly by weak sunlight, since Jupiter receives so little of it compared to Earth. The storm below seemed like it would have no real effect on the thin gas floating dozens of miles above it. That assumption turned out to be almost completely backward. The storm that refused to be boring, scientists targeted the upper atmosphere above the Great Red Spot, expecting almost nothing interesting. Jupiter receives only about 4% of the sunlight that reaches Earth, so researchers predicted this high-altitude region would look smooth and uniform across the entire area, since there simply should not have been enough energy input to create complex structure. Team leader Henrik Malin of the University of Leicester later admitted the assumption going in was that this stretch of atmosphere would be dull. Instead, Webb's instruments picked up dark arcs and bright glowing spots scattered across the entire field of view, forming intricate patterns nobody had documented before. The area above the Great Red Spot turned out to be just as active and detailed as Jupiter's polar auroras. According to the same research team, even though nothing in that equatorial region should have been generating that kind of energy on its own. Sunlight explained part of the glow, but not the complicated shapes twisting through it. The best explanation researchers have offered involves something called gravity waves, a type of atmospheric ripple similar to waves rolling onto a beach. These waves form deep in Jupiter's turbulent lower atmosphere, likely stirred up by the enormous storm system of the Great Red Spot itself, then travel upward through the layers above, changing the structure and brightness of the gas as they pass through. The results were published in Nature Astronomy in 2024, and the team is already planning follow-up observations to track how these wave patterns shift and move over time. That explanation, however, only accounted for one region of the planet. A separate discovery near Jupiter's equator would soon reveal that the entire upper atmosphere was moving in ways nobody had mapped before. The jet stream hiding in plain sight. While one team studied the Great Red Spot, another group using Webb's near-infrared camera found something entirely different sitting right over Jupiter's equator. At a wavelength sensitive to altitudes between about 12 and 21 miles above the main cloud layer, researchers spotted a jet stream stretching more than 3,000 miles wide, a scale so large it would stretch across the continental United States and beyond. The jet moves at roughly 320 miles per hour, which is about twice the sustained wind speed of a Category 5 hurricane on Earth. It sits around 25 miles above Jupiter's visible clouds, deep in the planet's lower stratosphere, a layer that had never been mapped with this kind of clarity before. Lead researcher Ricardo Hueso of the University of the Basque Country described the finding as something that genuinely caught the team off guard, since nothing in prior observations had hinted at a wind current this fast or this wide sitting in that particular layer. By comparing Webb's high-altitude wind measurements to older data from the Hubble Space Telescope, which observes deeper cloud layers, researchers could calculate how dramatically wind speeds change with altitude in Jupiter's atmosphere. That comparison is giving scientists their first real look at how the different layers of Jupiter's turbulent atmosphere interact and exchange energy with each other. The findings were published in Nature Astronomy, adding one more piece to a puzzle that kept growing stranger with every new observation. But the most dramatic surprise waited at Jupiter's poles, where the auroras themselves turned out to behave nothing like scientists expected. The lights that change faster than anyone thought possible. Jupiter's auroras have been studied for decades because of how enormous they are. The dancing lights near Jupiter's poles are hundreds of times brighter than Earth's northern and southern lights, driven by that extraordinarily powerful magnetic field, pulling in charged particles and slamming them into the upper atmosphere. On Christmas Eve of 2023, Webb captured a new round of observations using its near-infrared camera, focused on a specific wavelength that reveals emission from a molecule called trihydrogen cation, written as H3+. This molecule forms when high-energy electrons collide with hydrogen gas, and it glows brightly in infrared light, making it an ideal target for Webb's sensitive detectors. What scientists found was emission that flickered and changed far more rapidly than anyone studying Jupiter's auroras had previously documented. Researchers had assumed these lights, while intense, would shift gradually over time, similar to how Earth's auroras evolve across minutes or hours. Instead, Webb captured fast-changing features that revealed a level of variability nobody had confirmed before. Researchers then compared Webb's infrared data against ultraviolet observations taken by Hubble around the same period, expecting the two datasets to broadly agree on what was happening in Jupiter's atmosphere. Instead, the comparison turned up unexplained discrepancies between what each telescope was recording, raising new questions about the particle interactions happening near Jupiter's poles. The research team has stated they now plan additional studies to understand exactly why the two telescopes disagree and what that gap in the data might reveal about Jupiter's atmosphere. That mismatch between two of the most advanced telescopes ever built has left one of astronomy's oldest Jupiter mysteries even more unresolved than before, and the strangeness did not stop at the planet's surface. The moons caught in Jupiter's crossfire. Jupiter's intense magnetic field does not just affect the planet itself. It also bombards the 4 largest moons orbiting nearby, and Webb's instruments turned out to be sensitive enough to detect the chemical fallout of that bombardment. On Ganymede, the largest moon in the solar system, researchers led by Samantha Trumbo of Cornell University detected hydrogen peroxide concentrated near the moon's north and south poles for the first time. That chemical forms when charged particles trapped in Jupiter's magnetic field strike the icy surface, breaking apart water molecules and reassembling them into peroxide, evidence of ongoing chemical damage happening on a moon covered in ancient ice. At nearly the same time, a separate research team detected sulfurous fumes on Io, the most volcanically active body in the solar system. Io's volcanoes constantly erupt sulfur and sulfur dioxide high above its surface, some plumes reaching hundreds of miles into space. And Jupiter's gravity is the main reason those volcanoes stay so active in the first place. The constant stretching and squeezing caused by Jupiter's pull, combined with tugging from neighboring moons, generates enough internal heat to keep Io's interior molten, even though it sits so far from the sun. Webb's detection of sulfurous gases added fresh detail to a process scientists had been studying since the Voyager missions first spotted Io's volcanic plumes in 1979. Researcher M.K. DePotter of the University of California, Berkeley, who helped lead the broader early release science program, pointed out that Webb proved capable of studying extremely faint targets sitting right next to an object as bright as Jupiter, something that pushed the telescope's engineering further than expected. Webb's reach extended even to Europa, the icy moon believed to hide a liquid ocean beneath its frozen surface. Observations confirmed the presence of carbon dioxide within that hidden ocean for the first time, a discovery that matters because it suggests the chemistry needed to potentially support life could exist far below Europa's ice. None of these moon discoveries were the original goal of Webb's Jupiter observations. They turned up almost as a side effect of a telescope sensitive enough to notice faint chemical signatures next to one of the brightest objects in the sky. What it all adds up to. Put it all together and a pattern shows up. A gas giant too cold and calm for complex weather is running an energy budget scientists still cannot explain, a puzzle dating back to Voyager in 1979. Decades of visits from Pioneer, Galileo, Cassini, and Juno never finished the picture. A region above the Great Red Spot expected to be empty was filled with structures as active as the polar auroras. A jet stream wider than the United States sat undetected the whole time. The auroras, already hundreds of times brighter than Earth's, flickered faster than anyone had confirmed, leaving Webb and Hubble disagreeing about the planet's own atmosphere. None of it was guesswork. The findings were published in Nature Astronomy and Science Advances. A telescope built to study the early universe ended up rewriting the rulebook for the planet next door. Jupiter earned its reputation as the best understood giant planet after half a century of visits. Webb proved that wasn't enough to see what was really happening above its clouds. If this video gave you something, subscribing takes 3 seconds and it helps us keep making content like this.